Hello class, this is Ms. Riggins with today's video on section 3.4, the chain rule. As you're watching the video, please remember to write down any important notes, equations, or patterns, as well as any questions you may have. Feel free to pause, rewind, or replay the video as often as you would like. As at the end of watching the video, please write down your video summary and a top question. Submit that via the online whisk before class. All right, let's begin. We kind of already been using the chain rule, but this section is going to talk a little bit more in detail about the chain rule. So the chain rule is really used when we're talking about composition of functions. Remember, one function depends on the other function values. So the rate of change of the composite function is basically equal to the rate of change of the outside function times the rate of change of the inside function. So you can't just look at how the outside function changes without considering how the inside function changes as well. And that's what we're going to use to differentiate using the chain rule. So let's take a look at two functions. We're going to call them f and g, where z is equal to g of x, where z depends on x, and then y is equal to f of z, where y depends on z. Well, if you recall, y depends on z, but z depends on x. So that's basically y is a composition function of f of g of x. Okay? So small changes in x will affect small changes in z, and then small changes in z will affect small changes in y. So basically, small changes in x will eventually affect small changes in y through z. And we call these small changes delta x, delta z, delta y. So small changes in x eventually will affect small changes in y. So if we want to take a look at how these changes are applied, we look at this algebraic statement. And it's a very popular trick of algebra, which is delta y divided by delta x is the same thing as delta y divided by delta s, but they've multiplied and divided both sides by delta z. And then they rearrange where the delta z is affecting. So if we take a look here, we can see that this first quotient, delta y divided by delta z, is basically saying as z changes, so does y change. And this second quotient here says as x changes, so will z, which makes sense. So when we put them together by multiplying, that way everyone's change is affected, so changes in x will eventually affect changes in y. Now, of course, dy dx is known as the limit as the delta x approaches 0 of delta y over delta x. So changes in y divided by changes in x. So I can rewrite this sentence as the chain rule of delta y over delta x as delta x goes to 0. So let's take a look, and this is what your book says. And again, remember that z is based off of g of x and y is based off of f of z. So the chain rule says that delta y over delta x is equal to, if you recall, the change in y based off the change in z with respect to the change in z, and then times the change in z with respect to the change in x. In other words, the rate of change of a composite function is the product of the rates of change of the outside function and the inside functions, as we can see right here. Your book further goes on and uses another notation that says if f and g are differentiable functions, then the derivative of the composition of f of g is based off the derivative of the function f based off the inside function times the derivative of the inside function. So in other words, the derivative of the composite function is the product of the derivatives of the outside and the inside functions. But the derivative of the outside function must be evaluated at the inside function. Now, I kind of like this notation to explain it because it's saying the derivative of f with respect to the g of x, i.e. the inside function, times the derivative of g with respect to x. Okay? And they talk about the outside and inner function. Let me erase it so you can see the statement. So let's take a look at these examples and see how we want to apply this. And there's two ways you can apply it. It's basically the same thing, but two ways. So here we have a function, which is basically a composite of functions, and we have our little inner function. If you want to take a look at it, let g of x be the inside function, and let h of x be the outside function. So f of x is the composition of the outside function of the inside function. So using our chain rule, we have to take the derivative of the outside function with respect to the inside function. So when we do that, 8 times whatever this inside function is, raised to the 7th power, and then we multiply it by the derivative of the inside function, which is, as you can see, the inside function is 3x fourth minus 2x squared, so the derivative of that function is 12x to the 3rd minus 4x. Multiply these two together, and we get something that looks like this in simplest form. Okay? Simple enough. Let's take a look at another way to do this so it won't get so confusing, which I like to call use substitution. So example 1. Well, I guess this is example 2. Let's differentiate this function, which is really a composite function. And we're going to call the inside function, and we call it u for some reason, 2 plus 5x to the 3rd. And the outside function is basically the inside function to the 5th power, so u to the 5th. So the derivative of y with respect to u is 5u to the 4th, and the derivative of u with respect to x is 15x squared. So according to the chain rule, we multiply these two things together. 15x squared times 5u to the 4th. Well, 15 times 5 is 75, and x squared times u to the 4th. And then at the end, we can basically replace u with what u is equal to, which is 2 plus 5x to the 3rd. And that's another way using, I call use substitution. Okay, that's it about the chain rule. As long as you know that when you take the derivative of a composite function, you take the derivative with respect to the function, and then take the derivative of the inside function with respect to the variable x, or whatever the situation may be. All right, that's it.